So we begin. Okay. So welcome everyone to this webinar to be delivered by Dr. Tarig Abdelgadir uh, from Loughborough University, UK. Before beginning this webinar, I would like to mention a few things. Um, so uh, this talk so usually our talks we stream it live on Facebook and but unfortunately because of some technical error we are unable to do it. But yeah, I mean, in case your connection is lost, you can again rejoin. That is okay. You can use the chat option to send the questions either to Manjil or to me, and then we will put them to the speaker. And the speaker has mentioned to us that he would like to keep it quite interactive. So you can send your questions and we will put it to him during the talk. And okay, so let me introduce the today's speaker.
I think
So
you've done so. It's just Tarig from Loughborough is sufficient. So.
okay, so yeah, so today's speaker is Dr. Tarig Abdelgadir, who is who's from Loughborough University. So okay, so and he's going to talk about an introduction to algebraic geometry. Okay, then we can begin.
Excellent. Thank you so much. It's a pleasure to do this. I've heard Fernando Villegas told me about the seminar and its existence, and I think he gave a talk here maybe a couple of years ago or something. Is that true, Manjit?
Yes. So he gave an interview.
An interview. Excellent, excellent. Yes. So yeah, I was sort of aware of the existence of this, and this is an excellent sort of initiative. Okay, so I'm delighted to be here. That's to say that. So I'm going to say a little bit about what algebraic geometry means to me. This is unfortunately going to be slightly chaotic, but I think this maybe makes the participants more secure, and somehow, hopefully, you can, I don't know, help guide the chaos towards something that you care about. And that will be fun. So this is basically my point of view in algebraic geometry. Please do not be put off algebraic geometry by this. Hopefully you'll be interested in algebraic geometry through this, but if not, then there are many aspects and facets to this beautiful area. I also don't want to come across as saying algebraic geometry is the best area in mathematics and the most beautiful and that. It's nice. It's just one of mathematics itself is extremely lovely, but algebraic geometry is one facet. But I'm going to start by saying, trying to answer questions that get posed to me in a party. So questions from dinner parties. So, or answers, maybe more like. So people ask me, okay, non-mathematicians ask me, oh, so you're a mathematician? Oh, great, okay, but I mean, and then obviously there's a progress of how hard these questions get. It's like, oh, but isn't all maths done? How can you do any research in maths? And then it's like, no, but some people ask even deeper questions, and they understand that research in maths is possible. And they ask, yeah, what area of mathematics? And I say algebraic geometry, and they ask me what that is. So I start by saying, okay, so remember from school, if we take P a parabola in the plane, plane like this, and L a line, find the intersection points. In PL. Okay, and so this is a question we get quite a lot in high school, right? I mean, we learn very quickly in algebra how to solve quadratic equations towards the end, and equations of a line and the like. And so again, here I'm being funny with what a parabola is. A parabola, am I defining it in a geometric fashion with a focus and the like, or am I defining it algebraically with different yeah, anyhow, being funny what a parabola is. But what I want to say is it ends up, so this, after sort of some work, you can sort of write the parabola is the set satisfying, so maybe I want to say, satisfies something that looks like y equals to ax squared plus bx plus c. And the line sort of satisfies or is defined by y equals to mx plus c. Obviously here I'm assuming the parabola is oriented in this way. I mean, I can sort of change coordinates and rotate the coordinate system to make it be whatever it is, but I'm just assuming that I have a nice set of coordinates where it looks like this. Yeah. And once I've got this, then I substituting, oopsie, I have this y, and if I substitute it into here, I get dot, 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 then one eventually gets an equation m1 x squared plus m2 x plus, I don't know, m3, and then you solve and find intersection points. Now, when in the point about this question is that what I'm doing here is I'm doing algebra. Right? At the end, I have a polynomial. Wait, I want this to be 0, right? I have a polynomial, and I'm trying to find sort of solutions of polynomials. But equivalently, we also get taught that this is just, you draw the parabola, you graph, and then you draw your line. This is P and this is L. And then you just find what the coordinates of these things are. And so it's also a geometric problem in a sense, right? So to solve the geometric problem, I translated it into an algebraic problem and solved the algebraic problem algebraically, and then translated it back into geometry to give you the problem, to give you the solution. And at this point in the party, I just say like algebraic geometry is doing this for high dimension or any dimension and any number of equations. And in a sense, I feel like that's at a sort of dinner party level. I think that's an honest introduction for what an algebraic geometry is. We have polynomials, and we look at where they're 0 or solutions of them, and we use algebraic techniques to tell us things about the geometry, and we use the geometry to enlighten us about the algebra. Okay, and so similarly, I mean, in another sort of vein, we can take 2 ellipses, and find their intersection points. An ellipse E1 will look like, or will be given by something that looks like x squared over a. Again, I'm picking a nice orientation, and I'm assuming it's centered in the origin, and E2 x squared over c plus y squared over d equals 1, and then we can play around with this. I'm assuming quite a lot, but the point is that here, what we end up getting is 4 solutions, because we have something that looks like that, and maybe something that looks like this, and you get 4 solutions there. Anyhow, the idea is we have algebraic, we have polynomials, and we have the 0 sets form the 0 set of this minus y, if I take the y to the other side, forms this parabola in R3, in R2, and these are the fundamental objects of what algebraic geometry is. Cool, so if there are no more questions, if there are no questions at all, I'll move on and try and do something a bit more formal. So maybe I like a bit of color, so I'll write the title, Algebraic Geometry, or maybe I want to call this Building Blocks. So the building blocks, as I said, are zeros of polynomials. And these things will be called, they're called algebraic varieties or algebraic sets. And so what does this mean? Given a set of polynomials, f1 up to fm, or do I take maybe this, inside some polynomial ring x1 up to xn. Here, maybe this is a field. So maybe take f equals to r or c, whatever you're comfortable with for now. Then the zero set, I'm going to define the vanishing locus for the zero set z of f1 to fm is equal to the set of x in fm such that fi of x is equal to 0 for all I. Okay, and so I just gave you an example of the thing before. If I take maybe x, sorry, if I take f to be y minus mx minus c, and so here n is 2, then this gives me a line in the plane. It doesn't need to go through the origin. It gives me some line. Yeah, this is the zero locus of f. Okay, again, I'm sort of being quick and fast with things, and we say an affine algebraic variety is a set of this form. So maybe I want this. No. No. It's a set of this form. Okay, and so this is the building block of algebraic geometry. The first fundamental objects of algebraic geometry are zero sets of polynomials. And the cool thing is that the way we relate this to, so if I have, let me look at the set of algebraic varieties. The way we relate this to geometry, and to algebra, is by taking the ring of polynomial functions and this gives us a finitely generated commutative ring. With no zero divisors. With no, I don't, yeah, here, no zero divisors or no potent elements. Anyhow, some type of ring is what you should be worried about. And from here to here, we do a similar thing to that, and we take zero locus objects.
Tarig, there are two questions.
Sorry?
There are two questions.
Excellent. Tell me.
So first question is by Abhishek, who asks, why was algebraic geometry needed? I mean, why or how was the field discovered?
To me, so algebraic geometry eventually became, somebody said, called something algebraic geometry probably in the 20th century, right? But its roots come from the Cartesian coordinates, right? In my opinion, the Cartesian coordinates are a way for us to graph things like this, right? As soon as Descartes started to graph lines and to graph parabola on the plane, this is when algebraic geometry started, in my point of view. So I hope that answers the question.
The second question is, what is a zero divisor?
A zero divisor is if I have, I wonder, so tell me where a zero divisor, yeah, if I have, let's look at this thing here. Let's look at Z mod 6Z, right? So I'm looking at numbers up to two numbers. I think of two numbers as being the same if they differ by a multiple of 6, right? If I multiply, so 2 in this thing here is non-zero, and also 3 is non-zero. Yeah, but if I multiply 2 and 3, I get 6. But in this little thing, 6 is 0, right? And so this is equal to 0. And so this thing here is an example of a ring that contains a zero divisor, because here what I've done is I've made two things multiply to give me two non-zero things multiply to give me a 0. And so this ring here has zero divisors. But if I was in a field, if I was just in the field of real numbers, I do not have zero divisors there. And in a sense here, I have to have some condition. If I was to define, if my geometric objects are only these, then the rings of functions will have some things that sort of, they inherit from the real numbers or from field properties. I hope that's. Please ask the same question again if it's not clear.
Okay. Yeah, thank you.
Now, and this question leads me very sort of naturally to modern algebraic geometry in a sense. So the question is, I mean, why this condition finitely generated and no zero divisors, maybe finitely generated, I like that condition, so I'm not going to ask why. So no zero divisors or integral domain or something like that, why? Well, the real answer is that in a sense, we can make sense of all of this without this condition. Without this condition. So basically, if I was to, what happens was, I mean, people start off with algebraic varieties and things that look like this, and this was like Zariski, maybe very early on in the 20th century. My history is not very good. But eventually it becomes somewhat clear that, I don't know, this is too restrictive, and one can make sense of this just being finitely generated or just being commutative rings. And here the corresponding thing becomes something called schemes. So this is almost basically due to Grothendieck and this idea of schemes or maybe affine schemes. I want them to be things that correspond to commutative rings or affine schemes. I also must say that if there are real, like honest algebraic geometers in the audience, they'll probably be disgusted with how sort of I don't know, careless I am with all these things, but I'm just trying to get an idea across. Okay, so somehow you can, it's the cool thing about this idea is that algebraic geometry is that for me as a student, is I've come across commutative rings at some point as a student, maybe not in these terms, but, and the fact that I can ask questions like, what is the dimension of a ring? Or when is a ring singular? Are these questions somehow made, maybe I should, here rings are commutative for me. These questions made sort of ring theory become so much more than what it is. I can now picture a ring. I can now understand sort of pinch points in a ring. I mean, that doesn't, in the algebraic definition of what commutative rings are, this is not apparent. Right? But introducing this geometry to it is super cool. And I think I wrote in one of, I don't know if when you guys apply to do PhDs, you have to write some personal statement and things like that. And I remember writing in my personal statement, I like algebraic geometry because it makes the algebra, it gives life to the algebra and makes it come off the page or something like this. I mean, this is very cringeworthy to me now as a grown-up, but in a sense, somehow it got me a PhD. I'm not sure that sentence got me the PhD, but in a sense, it did not impede me getting a PhD. So you get this really nice correspondence between two areas of mathematics that seemingly are unrelated. And I think in mathematics, we have, in the philosophy of mathematics, we all believe that mathematics is somewhat one idea, and all these areas are just ways for a human being to sort of break the task of understanding something into smaller things. And we all, I think, take lots of joy from ideas that combine or intersect these two seemingly unrelated areas of mathematics. And I think algebraic geometry is one such idea or one such bridge between two seemingly unrelated areas of mathematics. I don't think we get taught this explicitly, but it's somehow implicit in everything we see. We are told that a beautiful theorem is a theorem that is somewhat unexpected that relates to different areas of mathematics, but this is not explicitly said in sort of philosophy. But anyhow, I stopped philosophizing. I'll move on. So, do I have space or do I not? So maybe I'll say this in words. Lots of work in algebraic geometry goes into trying to translate geometric ideas into algebraic ideas and vice versa. And so maybe I'll say the next. I'll say in the next slide. So maybe. Oops. Algebraic geometry might seem a little too rigid. Basically, the topology, and I didn't tell you what that is, but the topology that naturally comes with it, naturally associated with it, is too weak. It doesn't have many open sets. Or maybe I'll write that explicitly so that we don't. It doesn't have enough open sets. What I'm trying to say here is that algebraic geometry is something that is related to polynomials, right? And polynomials are your first example of something smooth in life, right? I mean, whenever you learn differential geometry or calculus, first thing you understand how to differentiate and integrate are polynomials. And so algebraic geometry seems to be based on something that's really simple. We don't have exponential functions a priori in algebraic geometry. We don't have the really cool smooth functions and elliptic functions that you get in sort of analytic geometry. And so it might seem a bit too rigid and maybe a bit simple, but it isn't. And I will try and explain why. So part of the reason, part of this sort of apparent simplicity implies that a lot of work.
So there's a question, sorry.
Please.
Yeah. So somebody asks, your rings need to be rings of polynomials in a finite number of indeterminates, right? Or can we generalize to rings like Z mod Z NZ, or is it Z mod NZ? I'm not sure.
Yeah, I will come to that. That's a very good point. And that's exactly where the versatility, maybe I will say this point now, in fact. That's exactly why algebraic geometry is cool, right? It's this versatility in this field. Like your colleague just asked, he asked this F, I mean, or this ring is ring polynomials in say, complex variables. But I could have equally tried to understand what algebraic geometry or rings here with, or algebras basically, that are over fields that are not R or C. It could be Z mod PZ. I could look at polynomials at Z mod PZ and look at their and number fields, the rational numbers, all of these things. This versatility in my coefficients and in the rings that I'm dealing with gives algebraic geometry quite a lot of power. So in a sense, understanding the zeros of polynomials in a finite field is somewhat, it's like I have a finite number of points, and yeah, it's not clear how to do the geometry. I'm sure combinatorialists and finite geometers like these sort of things, but for a geometer, it's not clear that this is beneficial for somebody who's purely a geometer. But yeah, that's a very good point that I will come to later. Is there another question, Misha?
I don't think so. No.
Okay.
Thank you.
No worries. So a lot of work goes into translating algebra to geometry and vice versa. So maybe I'll try and, so this is something that I find very cool that I might try and demonstrate. So what is the tangent space to a source scheme? Maybe there's something that I should have said here that I didn't say. So I remember I told you something about these relating to these via rings of polynomial functions and vice versa being zero locus. And something I should have said is that morphisms here go to morphisms in the other direction. So this is the ring of functions associated to y, this is the ring of functions associated to x. And when I have a morphism from x to y, when I flip it through this correspondence, it flips the order. It's like what's called a contravariant functor. Okay, so what's the tangent space to a scheme? Let's first even ask what are the points of an algebraic variety or any geometric object, manifold, or any geometric object. Geo. So you can think of this is somehow an idea that maybe has analysis in its heart, but so the set of points on, say, on a scheme, let's call this X, on X is the same thing as the morphisms from point to X. This is just, oh my God, I'm running out of battery. It was 100%. Hold on. Okay, we're back in business. So, yeah, this is sort of a, it's an obvious idea that points on a geometric objects are the same thing as a map from a point to X, but it's a sort of slight change in mindset. And so the tangent space, maybe I don't need. Of say X at a point X is going to be given by something else. But let me, before going to that, try and unravel a little bit of what happens here. In algebraic geometry, like I said, maps between geometric objects correspond to maps between rings. And in this case, if X is an affine scheme, say, or affine variety, what happens is that I get, right, like I said, I flip the order of the morphism. And so I get that it's a map from OX, the ring of functions on X, to the ring of functions on a point. And the ring of functions on a point happens to be, right? If I have a point, the functions on it are just given by constants, right? I define what the constant is on that point, and that gives me. So I have something that looks like this. And the tangent space, again, the tangent space is, I don't need to look at the set of tangent spaces. The tangent space actually ends up being something that looks like OX, mapping to the ring, maybe F, with epsilon divided by epsilon squared. Now let me unravel what this means. This is a slightly delicate idea. So this ring epsilon minus epsilon squared, I should think about it as functions. So maybe I had to, so if epsilon mod epsilon squared, this, or maybe I will do this. The geometric space corresponding to it should lie on epsilon, on the line with coordinate epsilon. But I'm asking for epsilon squared to be 0. In normal geometric terms, this would mean that epsilon has to be 0. But I'm not asking for epsilon has to be 0. I'm asking for epsilon squared to be 0. I'm asking for a number so small that its square is 0. Yeah, and so basically this looks like a very small neighborhood of epsilon, of the point 0 in this coordinate space as a geometric object. And I'm looking for maps from this very small neighborhood, in a sense, to, so this ends up being a map from X to whatever it's, this, we call it spec when we take the other, when we associate a geometric object to a ring, to, oops, the other way around, right? It flips. To X. And so what this is I'm sort of probing. So if I have my space, oops, I have my space X, and I have it, I can make sure that I'm looking at maps from here to there. And so what that gives me is, inside here, I just have little arrows or linear approximations. In the sense, what a tangent space is a linear approximation of your geometric object. And linear means that I don't, every term that's of higher order has to vanish. And basically, a higher order vanishing means that epsilon squared is equal to 0. Yeah. So maybe let me tell you what this is. This is the set epsilon in whatever my field is, such that epsilon squared is equal to 0. So I really want to distinguish this from the set where epsilon is 0, right? And this is where sort of the algebra gives you more power than the geometry. I'm happy to take questions here because I understand this is a delicate point. If there are none, I can carry on. Okay, I'll carry on. So somehow the algebra, we can, this is the algebraists trying to get around and translate a geometric problem into algebra, but we have to sort of work a little bit hard. We have to translate things around and find this crazy geometric object and the like, but still we can get around a lot of the ideas in geometry that maybe do not have obvious translations to the algebra, and we can make that happen. And in a sense, that is super cool as well, because it gives the algebra, again, life, right? I can understand what singularity is. I can understand what dimension is through ideas of this form. Okay, I'll move on and say, do I want to say this here?
There's a question from my end.
Please.
So instead of having epsilon square, what if you replace it with epsilon cubed or a higher power of epsilon?
You could do that, and in a sense, there is how do you understand? Remember, I said here, this is a very good question, because here we said we don't have enough open sets, right? Our open sets in algebraic geometry, we can't really take a small neighborhood around X. But the way we do that is we take higher order approximations. So a small neighborhood is basically a formal, very, very small neighborhood is taking very, very high approximation, and that gives you some sort of Taylor series in a sense. And you can then understand what it means to be a small neighborhood of a ring, right? You just map this thing into, this thing into X, and then you change this to 3, and you map it into X, and you change it to 4, you map it into X, and you get higher and higher order approximations of what you're doing. And eventually, if you're lucky and your scheme is nice, you're able to create some open neighborhood of what's going on. Some sort of Taylor series like approximation. But in the Taylor series, if you cut the Taylor series at the level 1 term, you get the derivative, right? And so this corresponds to doing that.
I see. So this sort of corresponds to taking a derivative, which is the classical idea of the tangent.
Precisely. So it corresponds to taking a derivative. Here, we're not, in algebra, really, we don't have the tools to take a derivative. We don't have limits. So we don't have the same way of saying what taking the derivative is. And this is our way of getting around limits, basically.
I see. So since you're only left with, so this is like a Taylor series expansion, and you're only left with the linear term here.
Precisely.
Okay.
That's exactly the idea.
Okay, thank you.
And so, what I wanted, I mean, this is just a small little thing that happens in algebraic geometry, but I wanted to illustrate is this, the power of having these extra rings around, right? Not only that, but I also wanted to illustrate how much geometry we can capture through that. And hopefully I've managed to make the point through. I think something I will say that I will not write, I don't wonder what sort of time are we talking, by the way? Oh my God. Something I said that I will not write is that there's a big theorem by Serre that says that it's called Gaga, which is pretty cool, Geometric, Algebraic, Geometric Analytic, or one of the other, some permutation of these. And it says that actually the algebraic category of manifolds is very close to the analytic category over C. You almost lose nothing by going to algebraic geometry, even though initially you seem to only work with polynomials, right? And again, this is something a bit similar to saying that, yeah, I can take Taylor series basically, but obviously I'm simplifying this quite a lot. Okay, so I want to I have 15 minutes left, and maybe I wanted to say something about moduli spaces, because this is a place I'll say something at the end. But let me try and relate algebraic geometry to other areas, just to illustrate how cool this is. So, so let me see. Yeah, maybe. Oops. The power of algebraic techniques comes from the versatility in choice of f or coefficients. I mean, we don't always have to have coefficients. We can work over arbitrary rings, but so for example, Fermat's last theorem can be stated in algebraic geometric terms, right? I mean, what is it? It's x to the, I'm going to do the 3 bit. Y3 equals to Z3 has no solutions in N, right? And so N is not a field, but I can translate, this is equivalent to saying that x to the 3 plus y to the 3 equals to z to the 3 has no solutions, no non-trivial solutions in Q, yeah? And I can also sort of translate this to sort of 1, basically. Has no non-trivial solutions. Correct me if I'm doing a stupid mistake. And Q is a field, and so this is a polynomial over the field Q. And all I'm asking, this is somehow you can think of this as some curve in Q2. And all I'm asking is, I want to make sure that this curve has no points beyond the ones that I care about, the trivial ones in Q. And obviously, Fermat's last theorem is a hard theorem, right? But the way Andrew Wiles proves it is uses quite a lot of geometric techniques and algebraic geometric techniques, and this is somehow me trying to draw a trivial way of restating Fermat's last theorem in algebraic geometry. And so this is, in a sense, this versatility in the choice of f. So I could have chosen f to be a finite field, as a colleague of yours has a number field. I can go periodic fields. I can be as creative as I want, and somehow this is pretty cool. And geometry somehow informs number theory in this way. But what I find even cooler is that sort of number theory informing geometry. Geometry. And the example, please give me a 5-minute warning when it exists. An example of this is something called the Weil conjectures. And so let me take X, some complex manifold or complex algebraic geometry, complex variety that's well behaved. Okay, and so I can sort of change coefficients into and express X in terms of FQ, where FQ is a finite field of the form of order such that FQ is equal to P to the N. Yeah? This is just me changing coefficients. The cool thing about working over FQ is it's a finite thing. So the number of points XFQ is less than infinity, right? FQ itself is a finite field that has finite order. I'm looking for things, equations in that. So an even smaller set than FQ or powers of FQ. And so I can count basically the number of points that satisfy this equation. So how many points does a line have in FQ to the 2? You know, that's a relatively easy calculation, and you can find where it is. I can't do it live in my head. Okay. And so if I call this an M, we can form a generating series of this form. So this from basically QQ to the is P to the M from equals to 1 up to infinity of NM Q to the M. Yeah, this is just some number, and this is just some variable. And now I form a generating series. And in well-behaved cases, in cases we care about, this is a polynomial. So it terminates. And NM are Betty numbers of, of X over the complex numbers. So forming this generating series, Betty numbers are just some, these are just some topological invariants. And so what I'm saying here is that I'm counting points over a finite field, which seems to be somewhat a basic operation, eventually informs me about the structure of the complex analytic manifold. And so in this way, I go somehow the number theory, which is things over a finite field, informs me a lot about the complex geometry. And let me just double check how am I doing for time? I've got 10 minutes. Brilliant. Sorry, let me stop this. Excellent. So in a sense, I wanted to mention the Weil conjectures because there are somehow this seminar is somewhat based in India, right? And so there's lots of modern algebraic geometry. Obviously, algebraic geometry in India have like a long history, but there's lots of modern algebraic geometry that used the Weil conjectures to tell us quite a lot of things about moduli spaces. And this is, I mean, obviously, this is only a small part of what happens. Only is the small part that I know. But let me tell you about another idea that's super powerful in algebraic geometry. Hopefully, it will take me less than 10 minutes. So this is called moduli spaces. So this comes from a need to parameterize or classify. I think I have also a friend of mine who worked in C-star algebras, and again, all of his research proposals, when they start, they say there's an innate human need to classify things, and so, in a sense, the moduli space idea comes from some natural property of humanity, but I think that's way too much philosophy. So, for example, let's just do some classification problems or examples. So let's classify all finite sets. And moduli spaces are supposed to solve this. So the solution, or the moduli space, all finite sets up to bijection. So the moduli space here is just n, right? Every finite set up to bijection is just the numbers 1 up to n, or the cardinality of the space gives you just exactly this, the finite set. And or if you want, you can do something very similar and you classify all finite dimensional vector spaces up to isomorphism. And again, the moduli space here is n, right? Dimension gives you everything about the vector space of every field. But I just want to finish off with this example because I really like it and it tells you quite a lot. Classify all triangles up to rigid transformations and similarity. So depending on how much time I have 5 minutes. Maybe I'll give you 30 seconds to think about how you would do that. So I have triangles. I want to classify all triangles up to sort of similarity. You could do that in many several ways, but what I would do is I will do it, we try to tackle this using side lengths. So for a triangle, we call this side A, B, C, okay? And A, B, C are the lengths of the triangle. So what we have is that A has to be less than or equal to B plus C. Yeah, the triangle equality on one of them. And B is less than or equal to C plus A. And similarly, A is less than or equal to, C. C is less than or equal to A plus B. Yeah? All side lengths must satisfy the triangle inequality. Also, I have the side lengths must be greater than 0. I should have maybe started off with that. Okay. And now, have I done everything that I need to do? Well, everything that satisfies this set gives me a triangle, but I'm looking at triangles up to rigid transformation and similarity. So similarity I haven't dealt with here because I can always scale and ABC and they will still be there. But so this is all triangles. So let me do A plus B plus C is equal to 1 to fix the perimeter, length of perimeter. This will fix an element in my equivalence class up to similarity. Right. So far what I've done, if I'm able to draw this, the numbers, if you want, I'm going to think about this. Let me use different colors. These are my coordinate axes. I'm trying to draw a picture in 3 dimensions, so bear with me. This is A, B, C. I'm taking 3-dimensional space. And these conditions means I need to focus on the top orthant. These conditions cut out a plane at height 1. And so if I take this condition and that condition, it gives me some triangle at height 1 in R3. Okay. And now the conditions here, these give me a smaller triangle in this thing there. Okay. But I haven't really, I'm allowed to swap A, B, and B and C. And in this definition, I will get different triangles. So I need to mod out by the symmetry group S3, right? to get a triangle up to get the right moduli space. So if I think about what S3 does to this small triangle, well, this is S3 and D3 are the same. So it's up to reflections like that. And what I'm left with is a small little triangle. Maybe I'll use a different color. What I'm left with is a small little triangle here. Let me draw it a bit bigger. I haven't really drawn the right angles. And now this is the moduli space of all triangles, up to rigid transformation and similarity. The cool thing is that what happens is that one of the points here corresponds to equilateral triangles. And these edges will correspond to isosceles triangles. These edges are identified, right? Because anyhow, and this will correspond to degenerate triangles. So degenerate triangles is allowing one of the sides to have length 0. Right? And if you think hard about this, you will find that, I'm not sure exactly what the curve looks like, but there is a sort of conic that cuts this here, and this will be right angle triangles. And so why is this interesting in algebraic geometry? I mean, in algebraic geometry, we are often interested in classifying some geometric objects. What ends up happening is this classification actually gives us a geometric object in its own right. So here we're classifying triangles, and we ended up with a triangle, right? The moduli space itself is a triangle. And the cool thing about having a space parameterizing this is that you have deformation and families. So for example, if I take a line in this little triangle, I can imagine having a family of triangles changing angles continuously, right? So if I take a path, if I'm an ant walking on this thing, then I am looking at continuous family of deforming triangles. And this idea, this geometric idea, is super powerful and is everywhere in algebraic geometry. And I use it very much, and lots of people use it very much. And in fact, there's an excellent school in India that works on moduli spaces of vector bundles, for example, and they've used the bioconjectures they've used the idea that I had here to compute geometric invariants about these moduli spaces. And these geometric invariants create generating series that link to number theory, and and I will stop here. Thank you.
Thank you very much. Do you have time for 3 questions? I think there are around 3-4 questions.
Okay, brilliant. Yeah. Go for it.
Yeah, okay. So one of the questions is, one can make, so it's a comment, one can make a comparison to the differential map of differential geometry.
The differential map of the differential geometry. Maybe I am too ignorant to know what the differential map is. So. Here, the differential, yes. When I'm doing smoothness, right? The differential of the map, yes, analogs of that exist in a sense, yes.
Okay. Another question is Weyl conjecture still a conjecture?
Oh, no, sorry. This is a theorem now proved by Deline. In the maybe 60s or 70s.
Okay.
But it's somewhat cool that it's still, people know it as not as Deline's theorem, but Weyl's conjectures. I mean, somehow it's nice that we give values to conjecture still. I mean, but anyhow.
So there are 2 general questions, but before getting to those, I will ask Manjul, are there any more questions to you?
No, I have sent it to you.
Okay. So so one question is, can you mention some real life applications of algebraic geometry?
Very much so. So there are, I will start with the ones that are the most abstract, because that's what I like. In theoretical physics or string theory, if you're interested in things like that, somehow people believe, again, shoot me if you're a string theorist, people believe that space is made out of 4 dimensions that are 3 dimensions and time, and some other very, maybe more dimensions, but these dimensions are tightly wound and small that we can't see. But these extra dimensions are given by something called the Calabi-Yau manifold, or Calabi-Yau variety. And physicists like to understand what's going on there and like to have proofs for what's going on there. And so algebraic geometry has been informed and informs this sort of pursuit. 1. 2, in sort of anything in algebraic number theory is very related to algebraic geometry, and sort of cryptography and the like are very, very tightly bound. Encryption and cryptography are very tightly bound with algebraic geometry from the number theoretical perspective. So other real life applications, there's something called combinatorial algebraic geometry, or sometimes we are interested in optimization problems in real life, and quite a lot of optimization problems can be phrased in algebrogeometric terms, and algebraic geometry has been somewhat powerful in that regard. As a pure mathematician, the number of links algebraic geometry has with other areas is already something that I find super interesting. Maybe I'll stop. I'll not say too much more philosophy.
So I think there are, I mean, on that note, there have been a few more specific questions, like somebody's asking, can we use algebraic geometry in graph theory? And another question is there any application of algebraic geometry to algebraic topology?
Algebraic geometry. I am sure both answers are true. The question is for me now, what do I recall are precise examples of? I think usually what happens, how algebraic geometry informs, say, graph theory. What happens is that algebraic geometry creates a moduli space of problems in graph theory of some form, and when they degenerate, they become very simple. Right, so you could potentially ask, how does a conic intersect a line? Well, a conic intersects a line in 2 points, but a degenerate conic is just a pair of lines, right? So I can move a conic of some form, an ellipse, and degenerate it and sort of deform it in such a way that it degenerates to a pair of lines. And once it's a pair of lines, it's very easy to answer the question that how does a line intersect a pair of lines? And it intersects at 2 points because every line intersects a line. But then you have to prove that in your degeneration, in your modular space, that certain properties remain the same. And so maybe in graph theory, you have a problem that's very hard for the general, but very easy in the degenerate case. And so you can create some sort of continuous deformation of problems up to the degenerate case and solve it algebraic geometrically. Usually, this is a common technique, but I'm not sure. So for example, I think Kontsevich proved some formula about counting certain solutions to some enumerative problem, and this enumerative geometry problem, I think, is related to many combinatorial. It's just, again, I do not know the precise connections, but I am pretty sure they do exist. Sorry.
So so how much time do you have? If
I'm happy to
take a few more questions.
Yeah, please go for it, please.
Okay, so I mean, so another is connection of algebraic geometry to algebraic topology. Somebody's asking about algebraic geometry and elliptic curves. So
elliptic curves are an example of an geometric object, right? I mean, it's elliptic curves. I want to sort of take the view that elliptic curves are intrinsic to algebraic geometry. And to number theory, they are somewhat extrinsic. I mean, they're introduced to number theoretical sort of applications by algebraic geometry. I want to sort of take that bias, but yeah, elliptic curves and the cryptography of elliptic curves is very algebro-geometric in nature. Elliptic curves are, over the complex numbers, are essentially solutions of polynomials of degree 3 in the plane. And so, yeah.
Is algebraic geometry related with complex analysis? So, Tarig, you're muted.
So complex manifolds are very much complex analysis. So we're gluing things over holomorphic transformations. And this Serge theorem of Gaga says that the complex manifold created from holomorphic gluing and algebraic complex manifolds are very, very close. And one can jump from one. In fact, I wanted to say a few things that are, I think what's cool about why we care about certain connections to algebra in mathematics is that certain theorems in one side are easier to prove than certain theorems in the other side. So there exists a theorem or several theorems in the algebraic geometry side that when translated through Gaga, gives you Gaga, Serre's geometric, algebraic, geometric, analytic, give you non-trivial results about complex manifolds and in complex analysis. And we do not know of a purely complex analytic proof in that sense. So there's a theorem, very famous theorem called bend and break that uses reduction to finite fields that cannot be done completely in the complex numbers. And so you get that. Another thing I wanted to, I mean, the power of a field of mathematics comes from this. And for example, if you only cared about the real numbers, the existence of the complex numbers is very, very cool, right? It makes you think that solutions to polynomials over the real numbers always, or a polynomial over real numbers always can be factorized into quadratic terms, right? Or less than quadratic terms. And so even if you only care about a certain field in your life, then I think other fields will always influence it. And algebraic geometry has very wide tentacles. I even think that it may be, it has wide tentacles, but I even think that you could easily make 2 or 3 or 4 courses in algebraic geometry for undergraduates that would all be interesting. But anyhow, but as in algebraic topology, as in number theory, as in all of these areas, algebraic geometry is not better than anything, but it's connected to quite a lot.
So I have a comment from my side. So since there was a question about link between algebraic geometry and graph theory, so recently in the past decade or so, there has been like a lot of non-trivial, like very old conjectures in graph theory and matroid theory, which have been solved by Jun Ha and his team and his collaborators using like very non-trivial techniques from algebra.
So how do usually the proofs go? I mean,
I do not know. I do not. So I have shared. So for everybody, I've shared a link to a Quanta magazine article on this in the chat. So okay, and maybe one final question. So this is a question we ask every speaker. So can you mention some good books to for a beginner to get into this topic?
I personally like Basic Algebraic Geometry by Shafarevich. One. So maybe I'll write it in the chat. Is that better?
So I'm writing, Tarig.
Okay. And also Miles Reed has a book called Undergraduate Algebraic Geometry by Miles Reed. That's also, different people have different tastes. So that could work. There's also a nice book, again by I think a lady called Karen Smith. Can somebody Google this? I think. Let me see.
Yes, I know this book. I'll write.
Ah, cool. I think I've not read this book, but I heard good things about it. And there's also a nice book by Francis Kerwan on algebraic surfaces. That's complex algebraic surfaces called or something. That's interesting. I mean, this is the problem with algebraic geometry now is there are too many books and too many resources. I think 4 is enough, and you can look beyond that. If you even type algebraic geometry PDF on Google, you'll get so many people teach algebraic geometry courses in the world, and they all very happily share their notes. And I'm sure you'll find somebody who aligns with you. But I think these 4 books are a good place to start.
So, okay, I mean, there is a new question, and I think this is a question that, I mean, yeah, I definitely should ask.
Excellent.
The question is, what are the contributions of Grothendieck to the topic of algebraic geometry?
So Grothendieck, it's almost everything I said here was very much Grothendieck. So Grothendieck made immense progress in, maybe I'll go here. When I was saying here, so this translation from like just these rings to any commutative ring is very much Grothendieck. Okay, scheme theory is very much Grothendieck. Another thing, deformation theory is also very, very much introduced by Grothendieck, and the idea of moduli spaces and how to define them in a canonical good way was introduced by Grothendieck. Also, Grothendieck also made huge progress into solving the wave conjectures. He never managed, because he was trying to make it he was trying to solve it in a beautiful way. It never came through. Deligne is a student of Grothendieck, and he did it I think Grothendieck was a little bit unsatisfied with the proof. I mean, it's a proof, but he maybe wanted to have a more illuminating proof. I don't know, but almost everything that happens in algebraic geometry from the 60s onwards is Grothendieck, and I hope I'm not offending anybody by saying that, but I think that's
okay. So I think I don't think there are any more questions. So with this, we would like to thank the speaker, and thank you very much for the wonderful talk, and for giving us your time and for answering so many questions.
I am very grateful for this opportunity, and I'm thankful to you guys for letting me speak. I hope it wasn't too chaotic, and hopefully somebody gets something out of this. Maybe I think this example of modular, this triangles business is very nice, and it's this very small paper in I think American Math Notes. It's called, let me find out, what is it called? Why do all triangles form a triangle? It's a nice paper if you are interested in this. Why do all triangles form a triangle? And this is by Ian Stewart. I mean, I think people are familiar with Ian Stewart because he's a popular math guy. And this is, in fact, can I attach a file here or no?
No, you cannot. Sorry.
Yeah, unfortunately, it's beyond the paywall. But so you don't. I mean, you have to have some sort of subscription. But if you can find it, it's a nice read. I mean. But, yeah.
Right. And also, before ending, I would like to advertise. I mean, this is like a really good setting to advertise our next talk, which is Sunday next week, which is by Professor S. Ramanan from Chennai Mathematical Institute, who's an expert in Moduli Spaces. And he'll be talking about classification problems in mathematics.
Super. I'm pretty sure he'll say something about triangles, but I am not sure, but I hope I did not step on his toes, basically.
Yeah.
Well, thank you guys so much for everything, and it's a pleasure. Thank you.
Yeah. So I'll stop the recording now. So Manjul, yeah. So he stopped the live stream. I'll stop the recording now.